We'll now look at an example comparing the direct map and the set associative caches. So consider a 4-line direct mapped cache, each containing one word block. So each of this is one word. And we want to find out the number of misses for this following sequence of instructions. So all of them are loads, which means they're all reads, and therefore they're all cache reads. And the addresses are given here. So ignore the format. Of course, the format has to be load word T0 and some address with S0, some register like this. But let us assume that the memory location finally is 0x00, that's in hexadecimal. So these are the sequence of instructions and addresses. So we'll see how to work this out. So 0, 8, 0, 6, and 8. So firstly, there are 4 lines. So you can work this out two ways. One is you can just do a 0 mod 4, 8 mod 4, and so on to find out which line the cache will go to. Or you can write out the address. Uh, Let us write this out in a 8-bit format, and then we can separate this out into index and tag and figure out where it goes. So let us look at both of those. So here you have 0 mod 4, which means you get 0, and therefore it will go into block 0, which is the first line. Then 8 is also going to go into block 0. So firstly, when you get address 0, there is nothing in the cache. Therefore, it's a cache miss. And you'll bring that line from the memory and put it into the first line of the cache. Then when you get 8, it's also giving you 8 mod 4 is 0. So it should also go in the same line, and it is a miss obviously because the data corresponding to 8 is not present, and therefore you will bring it uh, from the memory and replace this 0 with 8. And then now when you get 0 again, you will it's a miss again, so you will replace this data with the data of corresponding to memory 0. When you get 6, so it is block 2, and the data is not present here, and therefore it's a miss, and therefore you will again bring that from memory and place it here. Now when you get 8, so it's again a miss because you currently have 0 here, and therefore you're going to bring it from the memory and place it in this line. So basically all of them are misses. So now let us erase this and then do it the proper way, which is the index and the tag way. So now there are 4 lines in the cache, which means the index bits are 2 bits and the rest are tag. I'm just assuming 6 bits here just to make it simple. So now 0. So what would you ideally do now? 0 is split now into index and tag. So the first thing is you will go into index 0. This is going to have data. uh, in fact, it's going to have um, a valid bit, it's going to have a certain tag, and it's going to have a certain data. Now you'll go into index 0, check for the valid bit. So ideally the valid bit should be 0 because there is nothing in the cache, which means that it is a miss, and therefore you would not do any tag comparison. And therefore you will now just bring the data from the memory and place it here and update the tag. Now the tag is 0000000. So that is the tag here. That is the end of the first address. So now the second address, 8. So you would split it up. Let me just write 4 bits for the tag because the rest are zeros anyway. So you're going to split this up again into index and tag. So this is index. You will go into index 0, which is this index. And the valid bit is 1 because you already have a data here. And you will now do a tag match. So the tag is 1 0 here, whereas here it is 0 0. The tag does not match, which means that uh, the data corresponding to address 8 is not present, and therefore it is a miss. So when you have a miss, you're going to bring the data from memory and place it here, and so on. So you can do the same for the rest of them. So finally, you have all misses here. So what happens if you do a two-way or two-line set associative cache? So 2 lines means there are 2 sets, and 2 ways means there are 2 columns here, each having their own tag and data. So let us repeat it for the same set of addresses. So again, let us do it the proper way. So you have address 0. So let me just put two more zeros here. So you split this up into index and tag. So there is only one index bit because there are two sets here. So this is the index and the rest are tag bits. So firstly, there is you go to index 0 and you will have a valid bit, tag bit, a valid bit and a tag bits. So now you will go into set 0 because index is 0. You will check for valid bits. Both of them are not valid, which means it's a miss. So you will bring the data and put it into one of these blocks. You can either put it in this way or in this way. Let us put it in the first way and update the valid bit, update the tag bits. 00000 is a tag. Now you get address 8. So repeat the same thing. So it is again one bit of index. So you will go into index 0 and you will try to do a tag match. First you will see the valid bits. This is valid and this is invalid, which means that there is nothing here and there is something here. So when there is something there, you're going to do a tag match to see if the data is already present. The tag will not match because uh, this is different from this, and therefore this is a miss in the first way. Second way is having an invalid bit, which means it is empty. Therefore, what you can do is bring the data and put it there. So this is a miss, but you don't have to knock off this data 0. You can always place it in the next way. Then now when you get 0 again, you have not knocked off the 0 previously existing. Therefore, when you do a tag match, it will match with this and it will return a hit. When you get the next address 6, so you will now see that 6 is 110. Let me put a few zeros here. So index is 0 and what you will do is go into index 0 and try to do a tag match. The tag will not match. And you also know that both of the ways are full, which means both the valid bits are 1. So now you have to place the data here corresponding to address 6, which means you have to evict one of these lines. So which of these lines will you evict? So now when you get the data 6, so it means that you have tried to find where to place it. So you have to evict one of these lines. You have to evict either 0 or 8. So which of these will you evict? If you follow a replacement policy, let us say you follow the least recently used policy, you will not evict 0 because it has been recently used. And the only other option is to evict 8 because it is the least recently used. So you're going to evict 8 and then place the data corresponding to 6 here and you update the tag. So the tag corresponding to 6 was 00011. So this way you're going to continue and then finally 8 is going to result in a miss. So now compared to direct mapped cache, you got one hit. Direct mapped cache had all misses. And the reason why you got a hit here is obvious because you have multiple ways in which you can place data. Now, I would like you to repeat the same for a fully associative cache. It is explained here. You can work it out yourself. So finally, to conclude, there are three types of misses. One is a compulsory miss, which means the first access to a cache block. The cache is initially you are starting the system and therefore there's nothing in the cache and therefore it has to be a cache miss. So even if you had an infinite cache, it will still be a miss. Then there is what is called a capacity miss, which means that you have a fixed size for the cache. You have a limited size, and therefore you cannot bring in everything into the cache, and that is limited by the capacity of the cache, and that's called a capacity miss. And the other thing is called a conflict miss. So conflict miss is what we have seen here. So if you go back to this, there is a conflict here between when you want to bring in data 6. So you have to either evict 0 or 8, and that is because you are going into the same index. So that is called as a conflict or a collision. And this can be resolved to some extent by changing the associativity of the cache or the size of the cache.